Have you ever gazed up at a clear night sky and spotted that hazy patch, wondering if it's just a distant cloud of gas or something far more extraordinary? What if I told you that faint glow is the Andromeda galaxy, a trillion-star behemoth hurtling toward us at breakneck speed, brimming with enigmas that could upend our grasp of the universe itself? Back in the early 1900s, the astronomical world was buzzing with a controversy that felt like a high-stakes puzzle, one where the pieces didn't quite fit the picture everyone had grown comfortable with. Imagine a time when the universe seemed neatly packaged within the borders of our Milky Way, a single sprawling galaxy that encompassed every star, every planet, and every wispy cloud visible in the night sky. But then there was Andromeda, that enigmatic spiral blur, challenging everything. Was it just a local nebula, a foggy patch of gas and dust drifting within our galactic neighborhood? Perhaps a stellar nursery birthing new suns right on our doorstep? Or could it be something wildly more profound, an entire separate galaxy, a distant island of billions of stars, implying a cosmos far vaster and more isolated than anyone dared to imagine? This wasn't just idle speculation. It was a rift splitting the scientific community, fueled by emerging telescope observations that hinted at distances and scales previously unthinkable. As astronomers peered deeper into the void, they spotted these spiral nebulae scattered across the heavens, their twisting arms evoking mystery and debate. Some dismissed them as interstellar debris, mere extensions of the Milky Way's reach, while others, gazing at their ordered structures and faint glows, suspected they were standalone realms, each a universe unto itself, separated by unimaginable gulfs of empty space. The roots of this showdown stretch back even further, to ancient stargazers who first noted Andromeda as a faint smudge in the constellation, named after a mythical princess. Persian astronomers in the 10th century described it as a small cloud, and by the 18th century, French comet hunter Charles Messier catalogued it as M31, mistaking it for a nebula to avoid confusing it with comet. But as telescopes improved in the 19th century, details emerged. Those swirling arms, dark lanes slicing through the light, and occasional bright flares that seemed out of place. Enter the early 20th century, where the debate ignited like a slow-burning fuse. On one side stood Harlow Shapley, a Missouri farm boy turned astronomer, whose journey into the stars began almost by accident, when he switched from journalism to astronomy, because the subject was easier to pronounce. By 1917, Shapley had revolutionized our view of the Milky Way, using globular clusters, those dense, spherical swarms of ancient stars orbiting our galaxy like loyal sentinels. He measured their distances with innovative techniques, concluding the Milky Way spanned a colossal 300,000 light-years, with our sun not at the proud center, but relegated to a quiet arm, far from the galactic hub. This made the universe feel immense, yet contained. To Shapley, there was no room for other galaxies. Those spiral nebulae, including Andromeda, had to be smaller, nearby phenomena, perhaps gas clouds or star-forming regions on the Milky Way's outskirts. He bolstered his case with observations from Adrian van Mynen, a respected colleague who claimed to detect Andromeda rotating over just a few years, implying it was close enough for such motion to be visible. Otherwise, its edges would exceed the speed of light, an impossibility under Einstein's emerging relativity. Shapley's confidence stemmed from more than measurements. It was a philosophical stance, a belief in a unified cosmos, where everything fit under one galactic umbrella. He pointed to the 1885 nova in Andromeda, a stellar explosion that briefly shone brighter than the entire nebula itself. If Andromeda were truly distant, that outburst would represent an energy output, defying known physics, outshining billions of stars in a flash. To him, the universe was a single, grand stage, and introducing separate galaxies would shatter that harmony, making our Milky Way just one dot in an endless sea. But opposition brewed from skeptics who saw inconsistencies in this tidy model. Leading the charge was Heber Curtis, a seasoned astronomer from the Lick Observatory, older and more polished in debate, with a knack for spotting flaws in the status quo. Curtis had spent years photographing and analyzing spiral nebulae, noting their uncanny resemblance to what the Milky Way might look like from afar, complete with dust lanes, bright cores, and those telltale arms. He argued these weren't local at all. They were island universes, a term coined by philosopher Immanuel Kant in the 18th century but now gaining scientific traction. Curtis's evidence was compelling. The novae in Andromeda appeared systematically dimmer than those in our galaxy, suggesting they were the same type of events but viewed from much farther away. If you adjusted for distance, the brightness matched perfectly, placing Andromeda millions of light-years out. He also highlighted the zone of avoidance, a curious band across the sky where no spirals appeared, aligning perfectly with the Milky Way's dusty plain. Proof, he claimed, that our galaxy's haze was blocking views of distant realms, just as Andromeda's might obscure its own vistas. Curtis didn't stop at visuals. He delved into red shifts, those spectral shifts indicating motion. Many spirals showed light stretched toward the red end, implying they were receding at tremendous speeds, far too fast to be bound to the Milky Way. Andromeda itself bucked the trend. Blue shifted and approaching us, but that only added intrigue, suggesting local gravitational dances amid a broader expansion. His view painted a universe of multiplicity, where galaxies like Andromeda were peers to our own, each isolated in the void, forcing astronomers to confront humanity's cosmic insignificance. The clash between these visions simmered through conferences and papers, but it boiled over on April 26, 1920, in the ornate Baird Auditorium of the Smithsonian Museum of Natural History in Washington, D.C. Dubbed the Great Debate, this wasn't a casual chat. It was a formal showdown organized by the National Academy of Sciences, drawing a mix of scientists, dignitaries, and even, rumor has it, Albert Einstein himself. The format was tight. Each man got 40 minutes to present, with Shapley going first from a typed script, laying out a broad astronomical primer before diving into his expansive Milky Way model. He spoke nervously, sticking to notes, emphasizing the galaxy's vastness and dismissing spirals as internal features. Curtis followed, more at ease, using projected slides and handwritten notes to dismantle Shapley's points one by one. He ridiculed the rotation claims as measurement errors. Anmanin's data was based on scant observations, over mere years too imprecise for such faint nebulous objects. On the 1885 nova, Curtis suggested it might be a supernova, a rarer, more powerful blast that could indeed outshine a galaxy if viewed from afar. The atmosphere was electric, the audience a blend of academics eager for resolution, and laypeople captivated by the cosmic drama. No live transcript survives, pieced together later from Shapley's annotated script, Curtis's slides, and their correspondence, but letters reveal the tension, Curtis urging a good friendly scrap to clear the air, Shapley preferring a gentlemanly discussion. When the dust settled that evening, no knockout punch landed. The debate ended in a draw, with both sides claiming victories in letters and follow-up papers. Published in 1921 by the Bulletin of the National Research Council. There they refined arguments. Shapley doubled down on Van Mynen's rotations and the nova's impossible brightness, while Curtis countered that novae might come in classes with Andromeda's being fainter due to distance, and that rotations were illusions from faulty plates. The scientific community remained divided, with lingering doubts about stellar energy sources. How could distant galaxies shine so brightly without nuclear fusion fully understood? And questions about why spirals clustered oddly, avoiding our galactic plane. Some astronomers hesitated, clinging to a single galaxy universe for its simplicity, while others pondered the implications for cosmology, evolution, and even philosophy. If galaxies were islands, was the universe infinite, or did it have edges? The stalemate didn't last long, thanks to Edwin Hubble, a former lawyer and boxer turned astronomer, whose work at Mount Wilson Observatory would deliver the decisive blow. Perched atop California's foggy peaks, Hubble wielded the 100-inch Hooker telescope, the world's largest at the time, scanning Andromeda for clues. In October 1923, he spotted a flickering star, initially thought a nova, but closer scrutiny revealed it as a Cepheid variable, a type of pulsating beacon whose brightness waxes and wanes predictably. This was gold. Harvard astronomer Henrietta Swan Leavitt had earlier established the period luminosity relation for Cepheids. The longer the cycle, the intrinsically brighter the star. By timing Andromeda's Cepheid, its pulse, spanning days, Hubble calculated its true luminosity, then compared it to its apparent faintness from Earth, factoring in interstellar dust. The result? A distance of about 900,000 light-years, well beyond even Shapley's bloated Milky Way estimates. But Hubble was meticulous. He hunted more Cepheids through 1924, refining calculations amid foggy nights and equipment glitches, eventually pegging Andromeda at over 2 million light-years away. Published in 1925, this wasn't just a number, it was a revolution, proving Andromeda a separate galaxy, the first definitively outside our own. The nebula theory crumbled. Spirals were galaxies. The universe a vast archipelago. Hubble's method, now a cornerstone of cosmology, opened floodgates to mapping the cosmos, revealing billions more galaxies, and even the universe's expansion via redshifts. Yet victory was bittersweet. Curtis was vindicated on multiple galaxies, but Shapley proved right about the Milky Way's size and our sun's peripheral spot. Our galaxy wasn't small, just one among equals. Van Martin's rotations, later debunked as measurement errors from imperfect photographic plates. The eighth, recognized as a supernova, capable of galactic brilliance. The great debate didn't just resolve Andromeda's nature. It humbled science, showing how evidence, even flawed, drives. It spurred telescope advancements, like the 2,000-inch Hale at Palomar, and shifted astronomy from galactic isolation to universal exploration. But as the cosmos expanded in our minds, so did the mysteries. What secrets hid within this newly crowned galactic giant, from its swirling arms to its shadowy core? Peeling back Andromeda's layers reveals a galactic titan that's far from the static swirl it appears to be from afar. A dynamic colossus shaped by billions of years of cosmic turmoil, with hidden architectures that whisper tales of violence and growth, each component a testament to the universe's relentless evolution. At first glance, through a backyard telescope, it looks like a serene oval haze, but crank up the magnification with modern observatories like Hubble or Spitzer, and you're staring at a barred spiral galaxy, precisely classified as Sas B in the Devacouleur Sandage system, stretching an immense 220,000 light-years across, based on the D25 isophotal standard, where its B-band brightness fades to 25 magnitudes per square arc-second, roughly twice the span of our Milky Way, though earlier estimates from the 1980s pegged it at 76,000 light-years, before infrared refinements expanded our view. That's no accident. Its structure mirrors ours in eerie ways, yet boasts quirks that set it apart, like a central bar of stars acting as a gravitational spine, oriented 55 degrees anti-clockwise from the disk's major axis, channeling gas and dust into feeding frenzies that birth new stellar generations. This bar, unveiled by the 2-micron all-sky survey 2 mass and Spitzer's infrared gaze, isn't just a structural beam, it's a dynamo, creating density waves that ripple outward, compressing interstellar material, and sparking star formation in rhythmic bursts. While its segmented nature, possibly flocculent with filamentary arms rather than perfectly continuous, hints at distortions from gravitational interactions, making Andromeda a living laboratory for understanding how spirals evolve from primordial gas clouds into mature cosmic whirlpools But don't picture it as a frozen painting. Andromeda is alive, its components locked in an eternal dance, driven by gravity's unrelenting pull, with a total mass now estimated at around 800 billion solar masses from escape velocity calculations, though dynamical models suggest it could tip the scales at up to 1.5 trillion, rivaling or even surpassing our Milky Way's heft, depending on the latest 2019 revisions. Zoom into the heart and you'll find the central bulge, a dense, glowing hub crammed with ancient stars, mostly red giants and dwarfs that have simmered for eons. Their light painting a yellowish core against the darker void, bulging out to about 1,000 light-years wide, and containing populations that formed in the galaxy's chaotic youth, when gas was plentiful and mergers frequent. This bulge isn't just a stellar retirement home. It's a cauldron of secrets, where Hubble's sharp eyes in 1991 first pierced the veil to reveal not one nucleus, but what appears as two, a brighter blob, dubbed P1, offset by about 5 light-years from the dimmer P2, creating an optical illusion of duality that puzzled astronomers for decades. Dig deeper with velocity dispersion measurements, showing stars whipping around at 160 kilometers per second. And it's clear, P2 is the true center, a compact disk of young, hot blue stars, possibly an embedded cluster called P3, whirling in a tight, eccentric orbit, trapped by a supermassive black hole, lurking at the very core, its mass refined in 2005 to between 1110 and 230 million times that of our Sun, far heftier than the Milky Way's Sagittarius A at just 4 million solar masses. This beast is classified as a low-luminosity active galactic nucleus, LLAG, detected mainly in radio and X-ray wavelengths, with flares noted in 2006, 2007, and 2013. Yet surprisingly quiet overall, not belching out the violent jets or quasar-like radiation seen in more ravenous counterparts. Instead, it subtly warps the paths of surrounding stars, accelerating them in ways that betray its immense gravity, without the drama of constant accretion. Astronomers speculate this odd double nucleus setup arose from a past merger, where an infalling galaxy's remnants got stretched into an elongated ring of old reddish stars encircling the black hole's domain, a hypothesis supported by computer simulations showing how such eccentric orbits could persist for billions of years, making Andromeda's core a gravitational oddity that challenges models of nuclear evolution and hints at a history of cosmic violence hidden in plain sight. Chandra X-ray observations add another layer, revealing hot gas pockets in the bulge enriched with heavy elements from ancient supernovae, suggesting the black hole may have been more active in the past, perhaps during a phase of rapid growth that sculpted the surrounding stellar landscape. Branching out from this bulging core are the spiral arms, those sweeping tendrils that give Andromeda its mesmerizing shape. But they're no mere decorations. They're bustling highways of creation and destruction, outlined by HA regions glowing with ionized hydrogen and traced in multi-wavelength glory. Infrared surveys from Spitzer and TUMAS show 2 primary arms emerging from the central bar, not smooth and continuous like a pinwheel, but segmented and patchy, with Walter Bade's 1940 studies describing them as beads on a string. Clumpy concentrations of young, massive stars and nebulae strung along density waves. These arms are labeled in detail, starting close in with dust-dominated N1S1 arms, lacking OB associations, progressing outward to N4S4 packed with HII regions and little dust, and fading into inconspicuous N7S7 with loose stellar groups at 23-24 kiloparsecs from the center. The arms wind outward in a grand spiral, separated by at least 13,000 light-years, with some models proposing a single dominant arm or a flocculent pattern of thick filamentary structures, rather than the classic 2-arm symmetry possibly warped by tidal forces from satellites like M3, which displace neutral hydrogen clouds from the stellar disk. Closer in, dust arms dominate, thick with molecular clouds that block visible light, but shine in infrared, hiding nurseries where protostars condense from collapsing gas. While farther out, OB associations, clusters of hot blue supergiants pepper the landscape, their stellar winds carving bubbles into the interstellar medium and ejecting heavier elements like iron and silicon into the surrounding halo. But here's where it gets intriguing. These arms aren't solid. They're density waves propagating through the disk at speeds different from the galactic rotation, like traffic jams compressing gas as they pass, triggering bursts of star formation that light up in waves, with ultraviolet images from Hubble, highlighting young blue star clusters, tracing the arm's edges. Recent studies even suggest alternative structures, such as overlapping rings or distortions from polar passages. And don't overlook the prominent rings. A massive ring of fire light years out, a cold dust torus brimming with star-forming potential and hidden from visible light by its opacity, composed primarily of molecular hydrogen and dust grains that absorb starlight and re-emit it in infrared. An inner dust ring, smaller and believed to stem from a head-on collision with M32 over 200 million years ago, stripping mass and creating tidal ripples, and even fainter outer rings detected in millimeter wavelengths, showing cool neutral hydrogen gas extending the galaxy's reach. These features hint at Andromeda's restless nature, where interactions reshape its very skeleton, with the interstellar medium adding depth, boasting at least 7.2 billion solar masses of neutral hydrogen, through to 140 million in molecular form, within the inner 10 kiloparsecs, and 54 million in dust, all raw materials for ongoing stellar birth, distributed unevenly with denser concentrations in the arms and rings. Enveloping it all is the dark matter halo, that invisible scaffold holding the galaxy together like cosmic glue, without which the whole structure would unravel into chaos. Its presence inferred from the flat rotation curve, where outer stars orbit at the same 250 kilometers per second as inner ones, defying expectations unless unseen mass provides the gravitational anchor. This halo isn't some ethereal afterthought. It's massive, outweighing the visible stars, gas, and dust by a factor of 10 or more, extending up to 1 million light-years outward, halfway to our Milky Way. And simulations indicate it formed concurrently with the galaxy from the Big Bang's primordial fluctuations, acting as a gravitational well that accreted baryonic matter over eons. Observations from X-ray telescopes like Chandra and XMM Newton reveal it's not just dark, it's laced with a hot gas halo, a diffuse plasma at millions of degrees Kelvin, estimated to contain half the mass of Andromeda's stars, about 400 billion solar masses, and enriched with heavy elements like oxygen and iron, from supernova ejections, with properties placing the galaxy in the green valley of the color magnitude diagram, the transitional phase where star formation wanes as gas depletes. This halo stretches into intergalactic space, its metallicity decreasing with distance, from metal-rich near the disk to near pristine at the edges, mirroring evolutionary paths shared with our Milky Way, where nearly half the heavy elements produced over its lifetime have been blasted beyond the 200,000 light-year stellar disk into this extended envelope. Yet puzzles abound. Why does the halo show such green valley traits, with supernovae polluting it unevenly? Theories suggest weakly interacting massive particles, WIMPs or axions, as candidates for the dark matter. But detections remain elusive, with gravitational lensing studies from Hubble showing how it warps light from background sources, confirming its clumpy distribution and role in stabilizing the galaxy against tidal disruptions. The halo's dynamics also influence Andromeda's future, as its vast extent will interpenetrate with the Milky Ways during their impending merger, potentially stripping gas and reshaping both. Orbiting this behemoth are the satellite galaxies, a retinue of smaller companions like courtiers around a king, each telling stories of Andromeda's dominance and hierarchical growth. with at least 14 confirmed dwarfs and potentially dozens more ultra-faint ones lurking in surveys from the Pan-Andromeda Archaeological Survey, PANAS. Leading the pack is M32, a compact elliptical just 8,000 light-years from the core, dense with stars, and possibly the stripped remnant of a larger spiral. Its high surface brightness and lack of young stars, suggesting a violent history where Andromeda's tides peeled away its outer layers during a polar plunge 200 million years ago, contributing to the inner dust ring and perhaps even triggering starbursts. Then there's EMA 110, a fluffy dwarf elliptical with a more extended structure, showing signs of ongoing low-level star formation and tidal streams of stars, trailing behind, slowly unraveling under gravitational harassment as it orbits at about 25. Deeper scans uncover tinier satellites like Andromeda, I through X-2003, ultra-faint dwarfs, barely visible with luminosities, 1,000,000 times fainter than the Sun. Their stars metal-poor and ancient, survivors from the universe's dawn, with ages exceeding 10 billion years, often aligned in a vast, thin plane spanning 1.3 million light-years, a plane of satellites that defies standard cold dark matter models, predicting random distributions, sparking debates over whether it's evidence of modified gravity, tidal dwarf formation, or a statistical fluke. These minions aren't passive. They fuel Andromeda's growth. Their gas and stars accreted over time, with simulations showing the galaxy has gobbled 100-200 low-mass systems in the last 12 billion years, blending their remnants into its halo and contributing to its 500 Ploggler clusters, dense, stellar balls, far outnumbering the Milky Way's 150, some young and anomalous, possibly captured during mergers, orbiting in patterns that trace past interactions. All this points to undeniable evidence of past mergers, cosmic cannibalism that has bloated Andromeda into the giant we see today, with its history etched in stellar archaeology visible through Hubble's panoramic mosaics, assembling over 600 fields to map coherent star streams, faint arcs of disrupted stars, like ghostly rivers, remnants of shredded satellites pulled apart by tidal forces over gigayears. The giant southern stream, for instance, stretches across 300, a tidal tail from a major collision 2 billion years ago, its stars showing mismatched velocities and chemistries that scream intruder, with metallicities higher than the halo average, suggesting it was a disk galaxy devoured from the inside out. Deeper scans with Hubble, Subaru, and the Canada-France-Hawaii telescope reveal huge clouds of stars in the outer halo, coherent structures indicating Andromeda devoured a massive progenitor galaxy, perhaps as large as 1/3 its size in an event dubbed the M32 progenitor merger, a near head-on smash around 2-3 billion years ago that reshaped its disk, thickened the bulge, and sparked widespread starbursts, scattering debris into shells and loops detectable in ultraviolet and visible light. Chemical fingerprints betray these events too. Pockets of unusual metallicity in the halo, isotopes out of sync with the main disk, such as elevated alpha elements from rapid star formation in the absorbed systems, suggesting multiple episodes of accretion that enriched Andromeda unevenly. Even the ring structures and offset bar hint at gravitational ripples from these encounters, with M32's polar passage creating ripples that persist today, and simulations using N-body models showing how such mergers can flip angular momentum, form counter-rotating streams, and even explain the plane of satellites as tidal debris aligned in orbital planes. Multi-wavelength views add color. Chandra's X-rays highlight hot gas bridges from recent interactions, while radio maps from the Very Large Array trace neutral hydrogen tails extending hundreds of thousands of light-years, remnants of gas stripped during flybys. These mergers aren't rare. They're Andromeda's growth strategy, turning it from a fledgling disk into a mature spiral, with each swallowed galaxy adding mass, angular momentum, and complexity, potentially triggering the central black hole's growth through binary mergers of their own supermassives. Yet as we map these scars and streams, fresh questions emerge about what chemical mysteries these violent unions have brewed within its depths, from the forging of heavy elements to the isotopic anomalies that fingerprint its turbulent past. Diving into Andromeda's chemistry uncovers a fingerprint shaped by billions of years of stellar fireworks, a cosmic recipe book where elements blend in ways that reveal not just the galaxy's past, but perhaps hints of worlds, yet unseen, a swirling brew that starts simple but grows ever more complex, challenging our understanding of how galaxies cook up the stuff of stars and planets, with each spectral line and isotopic quirk acting as a breadcrumb trail through eons of evolution. At the foundation lies hydrogen, the universe's most abundant element, dominating Andromeda's interstellar medium, with an estimated 7.2 billion solar masses in its neutral atomic form, Hi, traced through 21-centimeter radio emissions from telescopes like the Very Large Array, and another 340 million solar masses locked in molecular hydrogen, H2, within the innermost 10 kiloparsecs, where dense clouds clump together under gravity's pull, often co-traced by carbon monoxide, CO, as a proxy, since H2 itself is invisible in cold states. This hydrogen isn't just passive, it's the raw material that collapses under gravity to ignite nuclear fusion in stellar cores, fueling the galaxy's ongoing star formation at a rate of about 1 solar mass per year, half that of the Milky Way, particularly concentrated in the spiral arms, and that prominent ring of fire at 10 kiloparsecs, where density waves compress it into cosmic pressure cookers, enabling the birth of massive star clusters and HII regions glowing with ionized gas. Alongside hydrogen sits helium, the second most common element, forged in the Big Bang's fiery aftermath, and comprising roughly 25% of the baryonic mass across the universe. But in Andromeda, its distribution tells a tale of uneven enrichment, with purer pockets in the outer halo, contrasting the metal-laced gas nearer the core, suggesting a history of gradual pollution from stellar deaths rather than a uniform mix, as evidenced by helium abundance measurements in planetary nebulae, showing He-H ratios around 1 to 0.1 relative to solar values, indicative of minimal dredge-up in low-mass stars, compared to more active galaxies. As stars live and die within this galactic forge, they weave in heavier elements, astronomers' catch-all term for anything beyond helium, collectively known as metals, that transform Andromeda's chemical landscape from a bland primordial soup into a rich tapestry of complexity, with the galaxy's overall metallicity, Z averaging near solar levels in the disk, but dropping precipitously to as low as 1/10 solar in the outer halo, as mapped by spectroscopic surveys of thousands of red giant stars, using instruments like the Hubble Space Telescope and the Sloan Digital Sky Survey's extensions. These metals, like carbon, oxygen, nitrogen, and iron, are born in the nuclear hearts of stars through fusion processes, with lighter ones, such as carbon, produced via the triple alpha process in helium-burning phases, and oxygen, synthesized in massive stars, neon-burning stages, emerging from the stable burning phases of mid-sized stars, while heavier beasts like iron and nickel require the cataclysmic explosions of supernovae, both core collapse type 2 from massive progenitors and thermonuclear type 1a from white dwarf binaries, to scatter them across the void, enriching the interstellar medium over generations. In Andromeda, this enrichment is evident in the galaxy's metallicity gradient, which slopes gently at 0.15 dex per kiloparsec, from the center outward, shallower than the Milky Way's LO 6 dex kpc, implying a more efficient mixing or less pronounced inside-out formation, with oxygen abundances peaking in the inner arms, where star formation has been rampant, showing OH ratios around 0.4 dex in HII regions, ionized by young O-type stars, as measured through emission lines like O3 at 507 otter. Iron, a key tracer of Type 1a supernovae, traces a different path, often depleted in older stellar populations, but abundant in supernova remnants, scattered throughout the disk, with recent Chandra X-ray observations, spotting iron-rich hot gas bubbles at temperatures of 10.6, 10.7 Kelvin, contributing to a gradient where fuel H decreases by about, and halo stars showing spreads from NOWO 2.0, 2.5 dex, reflecting multiple epochs of accretion. This gradient isn't smooth, it's punctuated by anomalies, like metal-rich pockets in the halo that scream of past mergers, where absorbed dwarf galaxies dumped their own elemental stockpiles, perhaps elevating U with fair ratios from R-process neutron-star mergers, enriching Andromeda unevenly and creating chemical fossils that astronomers decode through absorption lines in stellar spectra, revealing how supernovae have ejected nearly half of the heavy elements produced over the galaxy's 12 billion year lifetime, beyond its 200,000 light-year stellar disk, into the extended halo, a process modeled in simulations showing outflows driven by supernova feedback at velocities up to. Other elements add nuance: neon, magnesium, silicon, sulfur, argon, and calcium, collectively alpha elements, show enhancements in the bulge, with indicative of rapid star formation bursts, where massive stars dominated before Type 1a supernovae diluted the mix with iron peak elements, as seen in planetary nebulae spectra, where argon abundances help gauge the initial mass function IMF of progenitor stars. Delving deeper into isotopic variations adds another layer of intrigue, turning Andromeda's chemistry into a detective story, where subtle ratios unlock secrets of stellar nucleosynthesis and galactic history, with high-resolution spectroscopy from facilities like the Very Large Telescope, VLT, and Keck, revealing fine details in atomic lines, isotopes, variants of elements with differing neutron counts, act as tracers. For example, the ratio of carbon-12 to carbon measured via millimeter wave spectroscopy of molecular clouds using ALMA shows enrichments in Andromeda's arms that suggest a dominance of massive stars' contributions, as these beasts produce more carbon-12 through triple alpha fusion in their helium-burning phases, with C12-C13 ratios around 60-80 in the disk, lower than the Milky Way's 90 due to more efficient mixing from mergers. Oxygen isotopes like O16 versus O18 reveal even more. In Andromeda, O16 dominates with O16-O18. 500, a hallmark of alpha process synthesis in core collapse supernovae, but variations in the halo, where O18 might be underrepresented by factors of 2 to 3, hint at contributions from asymptotic giant branch AGB stars, those bloated elders that dredge up material from their cores via thermal pulses and expel it in gentle winds, rich in S-process elements like barium and strontium, contrasting the violent blasts of core collapse supernovae that favor lighter isotopes. Spectroscopic surveys, such as those from the Sloan Digital Sky Survey's extension to Andromeda, and the Pan-Andromeda Archaeological Survey, PANDAS, have pinpointed unusual ratios in globular clusters like RBC, a metal-poor outlier with an iron abundance of Phi-trino, about 1/800 that of the Sun, and 1/3 the previous record for GCs, challenging the idea of a metallicity floor around Phi-trino, and suggesting that massive clusters could form in extremely low metal environments, perhaps aided by rapid accretion during the early universe, when gas was pristine and cooling inefficient. Magnesium, another alpha element, shows depletions in some clusters, with Mb-trino dipping to 0.3 or lower in second-generation stars, possibly tied to multiple stellar populations within GCs, where proton capture processes at high temperatures deplete magnesium while enhancing aluminum, as seen in Hubble phase, spreads up to pi 1.0. Andromeda's GCs exhibit now Atari enhancements up to a signature of this internal chemical evolution, driven by hot bottom burning and intermediate mass AGB stars, with some clusters showing anti-correlations between sodium and oxygen that span mirroring patterns in Milky Way GCs, but with greater extremes due to Andromeda's more massive progenitors. These isotopic quirks aren't uniform. They vary radially, with the bulge showing higher C-phi and K-psi of E ratios from rapid star formation bursts, while the outer disk leans toward contributions from slower evolving stars, painting a picture of an inside-out formation where the core built up quickly from metal-poor gas, and the arms lagged, influenced by gas inflows from mergers that diluted or enriched regions unpredictably, as modeled in chemical evolution simulations, predicting a mean disk age of 7 to 8 billion years, with metallicity peaking at H hour Pinacere 0.2 in the inner ring. No discussion of Andromeda's chemical mysteries would be complete without the dust grains, those microscopic architects that influence everything from star birth to potential planetary cradles, composing about 54 million solar masses scattered throughout the galaxy, primarily in the form of silicates, amorphous MbF compounds, and carbonaceous particles, graphite and PAs, that absorb ultraviolet light and re-radiate it in the infrared, making them glow in Spitzer and Herschel maps, with temperatures ranging from 15K in cold outer clouds to 50K in active star-forming regions. These grains aren't inert. They're forged in the atmospheres of AGB stars through condensation of metal vapors, and in supernova, ejecta via rapid cooling of shocked gas, with silicate varieties, rich in magnesium and iron, forming rocky cores that could seed terrestrial planets, while carbon-based ones, like polycyclic aromatic hydrocarbons, piscenes, emitting at 3.311 mmHg, dominate in carbon-rich environments, where COA1, their abundance peaking in the ring of fire, at 10 kiloparsecs, where dust mass fractions reach in shielding molecular clouds from destructive radiation, and allowing complex molecules like methanol and formaldehyde to form in icy mantles. Dust plays a pivotal role in cooling gas clouds, enabling gravitational collapse into stars by radiating away heat via far infrared emission. And in Andromeda, its distribution traces the spiral arms and rings, with denser concentrations in the inner disk, where mergers have stirred up material. Simulations suggest dust from infalling satellites contributes 10 to 20% to the total, potentially seeding planet-forming disks with the building blocks of life, including prebiotic compounds like glycine or water ice, clinging to these grains, as inferred from mid-infrared spectra, showing water absorption features at 3 MISOP. Variations in dust composition add to the enigma. Outer regions show more pristine, metal-poor dust, with higher aliphatic hydrocarbon fractions, while the core boasts enriched silicates from repeated stellar processing. An isotopic analysis of meteorite analogs suggests dust from Andromeda-like galaxies could carry signatures of R-process elements like gold and platinum, forged in neutron star mergers, and sprinkled into the mix at rates of 1 per 10 to 5 years, with dust-to-gas ratios dropping from 0.01 in the disk to 0.001 in the halo, due to sputtering by hot gas. This dust also affects the galaxy's overall evolution, locking away heavy elements in refractory forms and regulating star formation rates. Models predict that as Andromeda ages, depleting its gas reservoirs at a rate of 0.5 men to year through outflows, dust will accumulate, slowing new star births by increasing opacity and pushing it toward a green valley phase. on the color magnitude diagram, where it's already transitioning with a specific star formation rate of 10Y1, influenced by supernova-driven fountains that recycle dust back into the disk. These chemical layers extend to Andromeda's vast halo, a diffuse envelope where hot gas, estimated at 400 billion solar masses, heated to millions of degrees Kelvin by supernova shocks and virialization, carries heavy elements expelled from the disk, creating a green valley composition that's neither fully active nor quenched, with simulations indicating it's a blend of primordial infall with fissible O3 and recycled supernova debris, elevating O following evolutionary paths, similar to the Milky Way, but with subtle differences in enrichment rates due to Andromeda's higher mass and merger history, which may have injected more alpha-enhanced gas from disrupted satellites. Chemical evolution models, like those computing the Galactic Habitable Zone, GHS, based on metallicity and star formation history, suggest Andromeda's optimal zone for terrestrial planets lies between 3, where Z is high enough, 0.52 solar, for rocky worlds, but not so metal-rich as to spawn deadly gas giants too frequently, with about 11% of its all-formed stars potentially hosting basic life-supporting planets, and centered in a ring at 1214 kiloparsecs, with a mean stellar age of not 7 billion years, and a star formation history peaking 810 gyre ago before a secondary burst, 24 gyre ago, triggered by a wet merger. Yet, mysteries persist. Why the metallicity floor in GCs, broken by outliers, like EXT8, with its extreme depletions in iron, and magnesium, Ki, E5, 3, forcing revisions to theories that massive clusters need metals for efficient cooling, via fine structure lines, perhaps indicating formation in dark matter, subhalos with rapid gas accretion, before reionization, isotopic anomalies in the halo, such as depleted deuterium, BH, Ath, 10My5, from Big Bang relics, diluted by stellar mixing at rates 10 times higher than in the disk, hint at uneven accretion, while sodium enhancements in GCs, NDHA, up to pi-0, point to internal pollution from evolved stars, with hot bottom burning, creating anti-correlations between sodium and oxygen that span 1 dex, and aluminum spreads, suggesting multiple bursts of star formation within single clusters. Comparisons to the Milky Way reveal Andromeda as slightly more metal-rich overall, at pH disk average pi-0, 0.1 versus 0, perhaps from its denser local group environment, fostering more mergers and thus higher supernova rates, but with lower magnesium in some regions, pi-4 suggesting a bottom-heavy IMF or delayed Type 1a contributions, as detailed in chemical evolution models, contrasting the two galaxies' disk formation. As we probe deeper with future missions like the James Webb Space Telescope mapping molecular fingerprints in far infrared with MIRI and NeuroSpec, or ground-based arrays like ALMA, resolving CO isotopologs, these chemical riddles could unveil not just Andromeda's biography, but clues to habitability across the cosmos, from the potential for carbon-based life in metal-rich arms to the survival of extremophiles in low-Z halo pockets. And lurking within this elemental symphony are stars that defy the norm, rare luminaries pulsing with even greater enigma. Scattered across this galactic canvas are rare luminaries that pulse with mystery, defying the ordinary rhythms of stellar life and offering glimpses into Andromeda's most extreme environments. Stars that erupt in fury, race at impossible speeds, or cling to ancient chemistries from the universe's dawn. Each one a cosmic outlier, challenging our models of how massive bodies evolve and die, their behaviors shaped by the galaxy's turbulent history of mergers, starbursts, and gravitational chaos. These aren't your everyday suns. They're the outliers, the rebels of Andromeda's trillion-star population, often tucked away in dense clusters or the galaxy's far-flung halo. Detected only through painstaking surveys with telescopes like Hubble, Spitzer, and ground-based giants such as Keck, the Very Large Telescope, VLT, and the Apache Point Observatory, where multi-wavelength observations peel back layers of dust and gas to reveal their secrets. Their presence hints at violent histories, supernova scars, gravitational slingshots, and chemical anomalies that make Andromeda a treasure trove for astronomers hunting the universe's wildcards. With each discovery, refining our understanding of stellar evolution, mass loss, and the potential for exotic remnants like black holes or neutron stars. Let's unpack these enigmas one by one, starting with the luminous blue variables, those temperamental titans that can outshine entire star clusters in a single outburst. Their instability a window into the precarious balance of massive stellar lives. Luminous blue variables, LBVs, often called S Doradus variables, after their prototype in the Large Magellanic Cloud, are among the most massive and unstable stars known, evolved supergiants or hypergiants, tipping the scales at 20 to over 1, with luminosity soaring past 1 million times the sun's up to 4.6 million. In extreme cases, like Eta Carinae analogs, making them some of the most luminous of all stars, and placing them in the S Doradus instability strip on the Hertzsprung-Russell diagram, where temperatures range from 10,000 K at lower luminosities to 25,000 K at the high end. These beasts live fast and furious, their lifetimes spanning just a few million years total, and mere tens of thousands in the LBV phase, driven by intense radiation pressure from their cores battling gravity, leading to bloated, unstable atmospheres that trigger dramatic variability, periodic outbursts, or they cool from scorching hot states to around 8,500 K, shedding outer layers in massive ejections at rates up to 10 more 4 solar masses per year, and rarer, giant eruptions that hurl material at speeds up to 1,000 km/s, creating expanding nebulae, visible for centuries and sometimes mimicking supernovae in brightness. In their quiescent state, they appear as B-type stars with unusual emission lines like Hi Phaida 10 and Phaida 2, but during strong active cycles lasting 20 years or more, they expand, redden, and brighten visually by 1-2 magnitudes, while maintaining constant bolometric luminosity, a hallmark behavior explained by 3D simulations, attributing outbursts to helium opacity variations, causing envelope instabilities. In Andromeda, LBVs are prized finds, because the galaxy's proximity, 2.5 million light-years, allows detailed study without the obscuration plaguing Milky Way examples. One standout is AF Andromedae, discovered in 1927 as HV 4013, with photographic magnitudes swinging from 15.3 to 16.5 over irregular cycles, later confirmed as an LBV through spectra, showing broad hydrogen Balmer and helium emission lines with P Cygni profiles, those telltale blue shifted absorptions, indicating outflowing winds at 100 E500 telemeters Sol. Alongside Phi C and Phi C Sol, features typical of LBV nebulae, AF, and has erupted multiple times, including major events in 1917, 1953, 1970-74, 1987-92, 1998-2001, and 2017, each brightening it by 1-2 magnitudes, while its spectrum shifts from hot B-type to cooler A-type, a hallmark of the strong active cycle, where bolometric luminosity stays constant, but visual brightness spikes as the star expands and cools, with photometric data from the local group Galaxies Survey, LGGS, showing variations up to 0.5 mag in V-band on shorter timescales. Nearby, A Andromedae, VAR 15, mirrors this behavior, identified in the 1970s as an LBV with similar spectral quirks, its outbursts linked to helium enhancements and nitrogen overabundances from core dredge-up, suggesting it's peeling away layers en route to becoming a Wolf-Rayet star, with infrared excesses indicating dusty ejecta from past events. Recent surveys have unearthed more candidates, JNO 04341 Men, as ANO, confirmed as an LBV in 2020 via near-infrared and optical spectra from the 3.5 Man Apache Point Observatory and 6 Man, showing typical Phi-2 and Phi-2 lines, plus photometric swings of 0.27 magnitudes in V-band, classifying it firmly in the club and allowing radius and luminosity estimates via spectral energy distribution, SED, fitting. Another, Elamos J00 discovered in 2019 on Andromeda's distant outskirts, some 22 kpc from the center in a possible faint spiral arm, shines at over 500,000 solar luminosities, with erratic brightness changes of 1.2 mag in V-band, its spectrum revealing hydrogen Balmer lines, PI emissions, and forbidden lines, indicative of a circumstellar nebula from past ejections, with outburst and quiescence phases, both lasting several years, fitting the LBV pattern of a periodic variability. Additional finds from 2015 include 5 new LBVs in Andromeda's disk, spectroscopically confirmed with Hi and Ferisecond lines in quiescent states, their SEDs showing temperatures around 15,000–20,000 K, and reddening from intervening dust, with some displaying weak active cycles of less than 0 on time scales under 10 years. A 2015 poster from the ESO meeting highlighted even more, using spectra from the Special Astrophysical Observatory to identify LBV features like broad H-alpha emissions and OI absences, emphasizing their role in mass loss. These LBVs are thought to be transitional phases for massive stars, stripping mass before exploding as supernovae, perhaps Type 1n, with hydrogen-rich ejecta, and in Andromeda. Their distribution, often in OB associations along the arms, points to regions of recent star formation, triggered by density waves or mergers, with dozens more candidates lurking in dense clusters, identified by their spectra in surveys like those from the Apache Point Observatory, where variability and emission lines distinguish them from B supergiants or yellow hypergiants. Their rarity, perhaps only a few dozen confirmed in Andromeda, makes each one the key to understanding mass loss in massive stars, with implications for black hole formation, galactic chemical enrichment through winds enriched in helium and nitrogen, and even the potential for supernova imposters that briefly mimic true explosions. Not far behind, in Drama, are the Wolf-Rayet stars, those stripped-down powerhouses representing the peeled cores of massive stars, their outer hydrogen layers blasted away by ferocious stellar winds exceeding 1,000 kilometers Cs and up to 5,000 kilometers Cs in some cases, exposing helium-rich interiors that glow with intense ultraviolet light, and emission lines dominated by helium, nitrogen, carbon, and oxygen, with subtypes WN, nitrogen-rich, from O stars, shedding envelopes, WC, carbon-rich, further evolved, and WO, oxygen, the rarest and hottest, at up to 200,000 K. In Andromeda, these hot 30,000, 200,000 K luminaries, often 10 to 20 solar masses, but originally 25, 60 solar masses, or more, are evolutionary endpoints for stars above 25 solar masses, with strong need-CO lines at 46.8, E-lines at 46.8, and broad emissions from ionized winds, creating mass loss rates up to 10 from by 5 solar masses per year. Their spectra showing P Cygni profiles and blue continua that make them stand out in ultraviolet imaging from Hubble's pan-chromatic Andromeda Treasury FAT survey, which has cataloged dozens across the disk. A prime example is the population in Andromeda's spiral arms, where FAT and LGGS data reveal bright WN stars and OB associations, their spectra dominated by N3 and N4 lines, indicating nitrogen enhancement from CNO cycle processing, with luminosities around 10.5, 10.6 LAs, and effective temperatures of 40,000, 50,000 K. These stars are short-lived, burning for just a few 100,000 to 1,000,000 years before core collapse into black holes or neutron stars. And in Andromeda, their distribution traces recent starbursts, with clusters like those near the Ring of Fire, at 10 kpc, hosting WC types, enriched in carbon, CSI, Co.4 from helium-burning phases, contributing to the galaxy's dust and metal budgets through their winds that eject up to 90% of their initial mass, forming ring nebulae detectable in infrared. Observations from Spitzer reveal infrared excesses around some, indicating dusty circumstellar envelopes from colliding winds and binaries. About 40% are in pairs with rare WO stars, thought to be progenitors of type Ia supernovae, due to their complete stripping showing OVI lines and temperatures exceeding 100,000 K. Their presence in Andromeda's halo is rarer, but a few outliers suggest capture from merged satellites, adding to the chemical diversity with S-process elements from their AGB precursors. And surveys estimate hundreds in total. Their ratios, WN and WC, APO 1.5, indicating a metallicity similar to the Milky Way's, influencing models of massive star evolution. Then there are the hypervelocity stars, cosmic speed demons hurtling through Andromeda at velocities up to fast enough to escape the galaxy's gravitational clutches of about 500 km off the disk edge, often propelled by close encounters with the central supermassive black hole via the Hills mechanism, where a binary star pair is disrupted, ejecting one at hypervelocity, while the other orbits the black hole, or by supernova kicks in asymmetric explosions within binaries. In Andromeda, these rarities are detected via proper motion studies, with Hubble's astrometry showing trajectories inconsistent with disk rotation, such as stars in the outer halo flung from the core during three-body interactions, their radial velocities exceeding 500 km Oz, and often aligned with the black hole's position. Examples include candidates identified in 2018 surveys from the PFAT program, with young, massive O or B types that shouldn't exist in the sparse halo, suggesting origins in the disk before being slingshotted out, their spectra revealing high helium abundances from rapid rotation or binary stripping. These wanderers carry chemical signatures of their birthplaces, like enhanced metals from ARM nurseries, and their study helps map Andromeda's gravitational potential, with N-body simulations predicting dozens more awaiting discovery, some potentially intergalactic travelers bound for the Milky Way. Shifting to cooler realms, carbon stars glow with a distinctive reddish hue in Andromeda's bulge and halo. Red giants or supergiants on the AGB, where third dredge-up processes have flooded their atmospheres with carbon from triple alpha fusion, forming molecules like CN, C2, and CH that absorb blue light, giving them R or C-type spectra, with carbon to oxygen ratios exceeding 1, often pulsating as Mira variables on 100. These stars, typically 1/8 solar masses, are key polluters, shedding carbon-rich dust via pulsations, and winds at rates up to 10.46 solar masses per year, enriching the interstellar medium for future generations and contributing to pH dust in the disk. In Andromeda, thousands have been cataloged via infrared surveys like 2MASS and Spitzer, with examples in globular clusters showing C-Phi enhancements up to POTH 1.0 in low metallicities, their variability monitored for mass loss rates, and some in the halo as relics from accreted dwarfs, their spectra revealing S-process overabundances like barium from neutron capture in the He shell. Among the oldest are metal-poor relics, ancient stars with few H, below 2 point, survivors from Andromeda's formative epochs, 10-12 billion years ago, clustered in the halo and globulars like RBC, E878, with few H, EUH, EH. Among the most metal-deficient known, their spectra revealing weak metal lines, strong hydrogen absorptions, and depletions in alpha elements, offering windows into Big Bang nucleosynthesis and early chemical evolution. Finally, magnetars lurk as neutron star remnants, with magnetic fields trillions of times detected in Andromeda via X-ray bursts from soft gamma repeaters and anomalous X-ray pulsars, their extreme magnetism decaying to power flares, equivalent to 1046 ERDs, with candidates and supernova remnants, suggesting a population from massive star collapses, 840 solar masses influencing galactic magnetism, cosmic rays, and potentially fast radio bursts. But even these pale next to the voids at its heart. At Andromeda's center hides a monster, a supermassive black hole, devouring quietly, far larger than our galaxy's own. Its presence betrayed not by dramatic flares, but by the subtle dance of stars trapped in its gravitational web, a silent sentinel, shaping the core's every motion and holding sway over the galaxy's innermost secrets, with implications that ripple through the entire structure of this spiral giant, from stellar dynamics to long-term evolutionary paths. This behemoth, often denoted as M31, an astronomical nomenclature, to parallel the Milky Way's Sagittarius A, weighs in at an astonishing 140 million solar masses, refined through decades of dynamical modeling, velocity dispersion measurements, and spectroscopic observations from telescopes like Hubble Keck and the Very Large Telescope, VLT, dwarfing Sagittarius A at just 4 million solar masses and placing it among the more massive known in spiral galaxies, though still modest compared to quasar hosts like those in Messier 87 at 6.5 billion solar masses, or even the 100 billion solar mass monsters in distant ellipticals, with its mass-to-light ratio implying a significant dark component dominating the nuclear region's potential. Earlier estimates varied widely. In 1993, it was pegged at 3 to 5 times 10^7 solar masses, based on initial Hubble data analyzing stellar motions. But by 2005, more precise modeling incorporating asymmetric drift and three-dimensional velocity fields pushed it to 1 point, with recent 2018 refinements confirming around 1.4 Ks 10^8 using stellar kinematics from integral field units and accounting for the asymmetric drift in the nuclear disk, where tangential velocities exceed radial ones due to rotational support. It resides at the heart of Andromeda's peculiar double nucleus, a structure first noted in ground-based images from the 1970s by astronomers like Ivan King, but vividly resolved by the Hubble Space Telescope in 1991 as two bright peaks, P1 and P, separated by about 5 light-years, 1.5 parsecs, in projection, initially sparking theories of dual cores, a recent galactic cannibalism event where a smaller galaxy's nucleus was absorbed, or even an ongoing merger remnant with binary black holes spiraling toward coalescence. However, deeper analysis in the 1990s and 2000s, including Hubble's Space Telescope imaging spectrograph, STIS data, revealed this as an optical illusion. P1 is not a separate entity, but the projection of an eccentric, apsidally aligned disk of older, reddish asymptotic giant branch, AGB, and red giant stars, lingering at the apocenter of their Keplerian orbits, around the black hole, creating a stellar overdensity that mimics a second nucleus due to longer dwell times at the farthest points, residence time scaling with eccentricity, as detailed in dynamical models, showing eccentricity AIA 0.3, 0.5, and a disk thickness of 0.1 pc. Meanwhile, P2 harbors the true center, a compact, flattened disk of young, hot A-type stars about 1 light-year across, and containing over 100 massive blue stars formed in a burst around 200 million years ago, dominating in blue and ultraviolet light, with spectra showing Balmer absorption lines, rapid rotations up to 160 kilometers says, and a total mass of about 10-4 solar masses, possibly triggered by a gas-rich minor merger that fueled an inward spiral of material. This configuration, vividly captured in Hubble's multi-wavelength mosaics and integral field spectroscopy from instruments like ISI and OSIRIS on Keck, is thought to stem from a past black hole merger or tidal interaction with a satellite galaxy like M32, where gravitational waves from coalescing holes kick stars into these elongated paths with recoil velocities up to 1, or perhaps from a resonant relaxation process, where stellar encounters gradually pumped up eccentricities over gig-years through vector resonant relaxation, as simulated in N-body models, showing how such disks persist without tidal disruption, stabilized by the black hole's gravity and the cluster's self-gravity. The black hole's influence sphere extends about 1 parsec, 3.26 light-years, encompassing roughly 10 million solar masses in stars within the nuclear cluster, density d 10·7 men, whipping them into Keplerian orbits with velocities up to 1,000 kilometers s. Near the event horizon, Schwarzschild radius is 0.003 pc for its mass. Measurements derived from high-resolution integral field spectroscopy on telescopes like Keck and the VLT, allowing precise mass estimates via the virial theorem, M-via V2R Reg, and confirming the hole's dominance without needing direct imaging. Though future extremely large telescopes like the 30-meter telescope or the European Extremely Large Telescope could resolve the event horizon shadow at 10 miles resolution, potentially revealing accretion disk structures. Despite its colossal mass, M31 is remarkably quiescent, classified as a low-luminosity active galactic nucleus, LLAGN, with an accretion rate a mere 10^5 to 10^4 of the Eddington limit, the theoretical maximum, where outward radiation pressure balances inward gravity, calculated as L at 10^46, or its mass and corresponding to the 0.0 Cenorbio. For typical efficiencies, emitting only faint radio waves at 6 centimeter wavelengths, detected by the Very Large Array with fluxes around per 1 meter Gs, and a flat spectrum ALA, ARA 0.3, and sporadic X-rays in the 0 far from the blazing jets and accretion disks of more active black holes like those in Seyfert galaxies, or quasars, where luminosities can reach 1045 ergs, and feedback quenches star formation across kiloparsecs. Chandra X-ray Observatory's 15-year monitoring from accumulating over 1 minute of exposure time across dozens of pointings with the OSIS instrument reveals a baseline luminosity of about 1036 ergs, equivalent to a few solar luminosities and consistent with advection-dominated accretion flows, ADAFs, where hot gas radiates inefficiently, punctuated by occasional flares spiking to 10, such as a record 400-fold brightening in 2013, lasting several hours with a hardness ratio, hard-soft counts of a magnetic reconnection event in infalling gas streams, twisted by the hole's spin, estimated 0.5 from iron K-alpha line profiles, or a stellar wind clump, accreted from the dense nuclear cluster at rates of 10^6 µ. These flares are rare, occurring perhaps once every few years, with durations from hours to days, and no clear periodicity, though a potential 200-day quasi-periodic oscillation was hinted in early data. Notably, the hardness ratio remains consistent between flaring and quiescent states. HR, suggesting a common emission mechanism like inverse Compton, scattering of optical UV photons from the stellar disk, or synchrotron radiation from a compact jet, rather than distinct processes like shock-heated plasma, though the flares are softer, greater low-energy fraction than those from Sagittarius A, implying differences in accretion disk physics, magnetic field strengths, B 10-6, G near the horizon, or inflow geometries. This quiet state puzzles astronomers. With such mass and a surrounding stellar density of 10·7 stars PC3, providing ample fuel via stellar winds, 10 miles Iowa total, and loss cone captures. Why isn't it more voracious? Recent multi-wavelength studies using Hubble's optical UV imaging, Spitzer's infrared maps, ALMA's sub-millimeter observations, and even NuStar's hard X-rays uncover a gentle feeding mechanism, long spiral filaments of dust and gas stretching up to 100 parsecs, 36 light-years from the core, and containing about 10 to GeV solar masses of molecular material, density funneling material inward in a rotational flow, starting far from the center and spiraling down like water circling a drain at angular momenta consistent with the bar's pattern speed, as visualized in combined datasets, showing dust lanes darkening Hubble views, extinction AV Abe 1 to 2 mag, and glowing in Spitzer's 3.6 inner bands, with temperatures of 20 to 50 K and pH 8 pHs at 7.7, composed of cold molecular gas, traced by CO 1 to 0 emissions at 1115 gigathertz, with light winds 50 to 100 TO, originate from perturbed clouds in the galactic bar, or inner ring, at 1 to 3 kp, twisted by magnetic fields, measured at 5 to 10 μgs via Faraday rotation, measures from VLA and differential rotation into Archimedean spirals that deliver material at a steady, low rate of 10 mA per SAR without overwhelming the whole, avoiding the violent feedback seen in brighter AGNs, where radiation-driven outflows, 10 to 3 km quench in flow, and star formation. Simulations suggest this cold mode, accretion possibly enhanced by the galaxy's past mergers, stirring up gas reservoirs 200–500 million years ago, evidenced by the young blue disk, keeps M31 in a dormant phase with occasional snacks from stellar winds in the dense nuclear cluster, providing 10 more 5 MURs of ionized gas, or rare tidal disruption events, TDEs, of stars venturing within the 0.01 PC tidal radius. For solar-type stars, predicted to occur every 10–10–5 years, based on loss cone refill rates, and briefly illuminating the core in X-rays. Peak LX A1043 ergs or S, and optical transients, decaying over months via fallback accretion. The black hole's quietude also influences its surroundings. Without strong jets or outflows, wind speeds 100 km/s, it allows the blue star disk in P2 to persist, potentially forming from gas captured during a minor merger 200 million years ago that triggered a 10·4m starburst with an initial mass function biased toward high-mass stars, while its gravity stabilizes the eccentric orbits in preventing wholesale disruption and maintaining the double nucleus appearance through resonant trapping. Interestingly, M31 was more active in the recent past. A 206 flare marked the start of an elevated flux state persisting through 2000, with post-gap observations from 2022, suggesting it may still be ongoing, possibly due to lingering accretion from that event or subsequent flares, highlighting the need for continuous monitoring with missions like XTP or Athena to understand duty cycles and transitions between states. Beyond this central giant, Andromeda, may harbor a shadowy population of intermediate mass black holes. IMBHs, elusive objects, bridging stellar mass remnants, 5/100 solar masses, and supermassives, millions to billions, with masses from hundreds to thousands of solar masses, up to 10^5 in some models, lurking in globular clusters, stripped galaxy nuclei, or the remnants of merged satellites, their existence hinted at by dynamical signatures like anomalous stellar velocities, cuspy density profiles, or faint X-ray radio emissions rather than bright AGNs, as direct detection remains challenging due to their low accretion rates. And the galaxy's distance of 2.5 million light-years. These IMBHs are theorized to form via multiple pathways. Direct collapse of massive gas clouds in the metal-poor early universe, at rates exceeding 1 MBO a year, in regions with high genes masses. Runaway mergers, in young star clusters where massive stars, 10 to 100 MBO, collide and collapse within 3 to 5 million years, due to dynamical friction, or the gradual buildup from stellar black hole binaries in dense environments through repeated mergers and gas accretion over gigayears, with Andromeda's rich cluster population over 500 globulars, twice the Milky Way's and including massive ones like G1 at 10.7 MPO, providing ideal hunting grounds as their high densities, 10^5, 10d6 stars PC3, facilitate such processes and retain IMBHs through dynamical binding. A leading candidate resides in G1 Mayal II, Andromeda's most massive globular cluster at 10d7 solar masses and 200 light-years across, located 30 light-years from the center in the outer halo, where Keck and VLT velocity dispersion measurements show inner stars orbiting at speeds of 25 to 30 kilometers cs, with a rising profile toward the core, implying a central dark mass of about 20,000 solar masses, with upper limits to 40,000 from Bayesian modeling, too concentrated for a stellar cusp or dark matter subhalo, and consistent with an IMBH, as N-body simulations demonstrate how it could prevent core collapse by heating orbits through dynamical friction, ejecting stars via slingshot effects at 10 to and creating a mass-segregated profile observed in color gradients. Another suspect is in B023, G078, a compact stellar system in Andromeda's halo, interpreted as a stripped galaxy nucleus, with a mass of 10 to 6 solar masses, and radius where Hubble astrometry reveals a velocity dispersion of 10 to 15 kilometers r, requiring a 10,000, 100,000 solar mass IMBH to stabilize its dense core. Saya, carry, immense tidal forces from the host galaxy with potential faint X-ray emissions, LX, carry a 10 to 35 erg-sars, 135 erg-sars, hinting at low-level accretion from intracluster gas. These hidden holes aren't flashy. They accrete quietly from intracluster gas at rates below 10, perhaps powering faint X-ray sources detected by Chandra, with luminosities of 1035, 1037 erg-sars, and radio counterparts from VLA. But their gravitational impacts are profound, altering cluster dynamics by scattering stars into high-velocity escapes, creating hypervelocity candidates at 5, creating velocity cusps, observable in proper motions with Gaia, precision, and potentially triggering binary black hole mergers that emit gravitational waves, detectable by LIGO for 10-100 Ben, pairs with rates 1 varade per cluster, or future space-based detectors like LISA, for IMBH binaries at 10, like the compact elliptical M32, a potential stripped spiral core with a mass of 10.9 MPAs and high central density, Muse and Virus P, integral field units, suggest a 2.5 million solar mass black hole at its center, an IMBH-scale object, if considered relative to its host's diminished mass, influencing stellar orbits with dispersions up to 100 km/s, and a EML ratio of 2 to 3, possibly surviving as a wanderer if M32 is fully stripped during its ongoing tidal interaction with Andromeda over the next billion years. As modeled in hydrodynamical simulations, surveys like those from the Pan-Andromeda Archaeological Survey, PANDAS, and Hubble's Advanced Camera for Surveys estimate Andromeda could host dozens of IMB, particularly in its extended halo, where disrupted dwarfs leave behind dense remnants with masses 10-3, 10-5, and velocity dispersions 5-20 kilometers. Their presence inferred from microlensing events, temporary brightenings of background stars as the hole's gravity bends light, with Einstein radia 10 AU for 10-4 Amadeus holes, and event rates of 10-100 per year in dense fields or anomalous globular cluster kinematics, with ongoing searches using Gaia astrometry to hunt for telltale wobbles in cluster centers, amplitudes 110 MEO, and future James Webb Space Telescope infrared imaging to resolve nuclear star clusters in satellites down to 10 PC scales. These IMBHs may play a key role in seeding supermassives like M31 through hierarchical mergers, as modeled in cosmological simulations where they grow via galaxy assembly at rates of 10-3 MEO per merger during Andromeda's major merger 2-3 billion years ago, contributing to its evolutionary history by providing seeds that coalesced in the bulge, potentially explaining the high M31 mass relative to the bulge's velocity dispersion cess. Wandering through the disk and halo are even more elusive stellar mass black holes formed from collapsed massive stars, progenitors, 2040 solar masses, depending on metallicity and binary evolution, potentially numbering in the millions given Andromeda's integrated star formation history of 10-11 solar masses, over 12 gear, and a supernova rate of, but a subset may be wandering IMBHs, or tight binaries, ejected from clusters, or the core at speeds 150-500 km/s via dynamical recoils. Their gravitational effects seen in microlensing events, where they bend light from background stars, causing brief magnifications, duration weeks for IMBHs. Detectable in optical surveys, like those from the Subaru Hyper-Suprime Cam or the Vera C. Rubin Observatory, with rates predicting 10-100 events per year in dense fields toward the bulge. Chandra's deep fields of Andromeda, totaling over 2 MINS exposure, have cataloged over 500 X-ray binaries, XRBs, and dozens of ultraluminous X-ray sources, ULXs, exceeding 10 to 39 ergs, above the Eddington limit for 10 EMS echo holes, LED F1038 ergs, suggesting beamed emission from super Eddington accretion, rate C0.1 EMS echo Ys. Relativistic jets, or IMBH candidates, with masses up to 1,000 solar masses, concentrated in the bulge, where 7 ULXs lie within 1,000 light-years, possibly influenced by its tidal field, and arms where young star formation provides donor stars, like red giants or main sequence companions, in high-mass XRBs, HMXBs, with orbital periods 1. These systems' impacts include disrupting planetary systems through gravitational perturbations, ejecting planets at 10 km/s with cross-sections 10 Weimer 3 PC2, or triggering localized star formation via outflow shocks that compress gas clouds at energies of 1051 ergs over their lifetimes, with some ULXs associated with supernova remnants, indicating recent formation from core collapse events, and others in globular clusters, suggesting dynamical capture. Binary black holes among them could merge, producing gravitational waves like those detected by LIGO from events at cosmological distances, e.g., with Andromeda's proximity offering a lab to study precursors via radio monitoring. For jet ejections, fluxes Nero 1 Nero Y at 5 GHz, or optical variability from tidal interactions, potentially detectable by the Square Kilometre Array or the Nancy Grace Roman Space Telescope. Overall, these hidden black holes, supermassive, intermediate, and stellar, pull Andromeda's strings from core dynamics to halo structure. Their quiet machinations, a testament to gravity's unseen power, subtly influencing everything from stellar orbits to galactic evolution. And as we peer deeper with advancing technology, they promise to unveil more about the dark underbelly of cosmic architecture, perhaps even bridging to multi-messenger astronomy, with combined gravitational wave and electromagnetic signal. Speaking of the invisible, something even more elusive binds it all. Dark matter whispers through Andromeda, like an unseen skeleton, an invisible force binding the galaxy's trillion stars, vast swirling gas clouds, and sprawling dust lanes into a coherent whole, without which its elegant spiral arms would unravel like threads pulled from a cosmic tapestry, its outer reaches scattering into the intergalactic void, in defiance of the gravitational harmony that defines galactic structure, a cosmic glue that dominates the galaxy's mass budget, outweighing visible baryonic matter, stars, gas, and dust, totaling beyond 1.2 by 10 to 11 solar masses, by a factor of 5 to 10, and shaping its very architecture through gravity's subtle, yet overwhelming pull, a phenomenon first inferred in the 1930s by pioneers like Fritz Zwicky, but vividly confirmed for Andromeda through the galaxy's unexpectedly flat rotation curve, where neutral hydrogen, Hi gas, and planetary nebulae orbit at consistent speeds of 200–250, defying Newtonian expectations of a Keplerian decline. Weit ein R down, or never 1–2, unless an extended, non-luminous halo provides the extra gravitational heft to balance centrifugal forces. This enigmatic substance, comprising about 85% of the universe's matter content, and detectable only through its gravitational signatures, bending light, accelerating stars, and stabilizing structures, plays a pivotal role in holding Andromeda together by counteracting the disruptive tendencies of rotation and internal dynamics. Without it, the galaxy's thin disk scale height, 300 pc, would puff up and disperse under its own kinetic energy, as evidenced by dynamical models like those using the Jeans equations, which show that the visible baryonic mass accounts for only 10–20% of the total dynamical mass within the virial radius of 300 kiloparsecs, roughly 1 million light-years, with dark matter filling the gap to reach a total halo mass of approximately 1, a figure derived from escape velocity analyses of halo tracers 5,550 km/s at 50 kpc, and comparable to, or slightly less than, the Milky Way's revised 1.5 by 1012 solar masses based on Gaia satellite kinematics and proper motion data of globular clusters. The dark matter's influence permeates every scale. In the inner regions, it bolsters the central bulge against collapse, maintaining velocity dispersions of the 70 km/s observed in stellar kinematics, while in the dip it ensures the persistence of spiral density waves that trigger star formation without the arms shearing apart. As simulated in hydrodynamical models incorporating dark matter potentials that prevent bar instabilities from dominating too quickly. Enveloping Andromeda like a vast, diffuse cocoon, the dark matter halo extends far beyond the visible disk's 200, reaching a virial radius of about 300 kiloparsecs, nearly 1 million light-years, and possibly farther to 1.32 million light-years. Based on Hubble Space Telescope observations of quasar absorption lines in the Project Omega survey, which map a ionized gas in the halo's circumgalactic medium, CGM, and reveal a massive reservoir of baryons intertwined with dark matter, containing half the galaxy's stellar mass in hot plasma, at temperatures of 10 enriched with heavy elements like oxygen, OVI absorption, and silicon, CIIV, from supernova outflows that trace the dark matter's gravitational wells. This halo isn't a uniform sphere but a complex extended structure, potentially prolate, elongated along one axis, with an axial ratio Q on 1.3-1.5, based on axisymmetric mass models. Applied to the kinematics of 91 globular clusters GCs and 15 dwarf spheroidal galaxies, VICs, in the outer halo, which serve as dynamical tracers probing the potential out to 150 kiloparsecs, suggesting a shape aligned with the galaxy's major axis, position angle 38 Bo, and consistent with cold dark matter, CDM predictions, where halos form triaxially through hierarchical mergers, reflecting the anisotropic collapse of cosmic web filaments that channel dark matter in foul, preferentially along major axes, as evidenced by the observed alignment of satellite galaxies in a thin plane. Thickness 20 kpc, spanning 400 kpc. This prolate configuration derived from Jean's equation solutions. Assuming power law density profiles, Ra-Teen Artemarther with algebra 3-4 in the outer regions, and maximum likelihood fits to line of sight velocities. Dispersion implies that dark matter particles, likely weakly interacting, massive particles, WIMPs, with masses on 100 GeA or axions in CDM paradigms, cluster more densely along the galaxy's plane, influencing satellite distributions, and potentially explaining the observed planar alignment of Andromeda's dwarf galaxies, e.g., which defies isotropic expectations in spherical halo models and hints at tidal formation during ancient mergers, or preferential accretion along the halo's major axis, a phenomenon replicated in hydrodynamical simulations, like illustrated in G, where 10% of Milky Way mass halos exhibit such alignments due to large-scale structure torques. The halo's global structure, as mapped by the Pan-Andromeda Archaeological Survey, PANDAS, using wide-field photometry from the Canada-France-Hawaii telescope, reveals large-scale substructures like the giant Southern Stream, GSS, a 100 kpc long tidal tail from a disrupted progenitor, and associated shells whose kinematics and density perturbations require a steep outer density profile. Ralgene Ardemar through 3.7, steeper than the canonical NFWO. Ardemar 3 falloff, suggesting an over-tidied halo, whose outskirts were eroded by past major mergers or tidal interactions with the Milky Way, as N-body simulations of satellite accretion reproduce these features only with such a profile, challenging standard CDM and favoring self-interacting dark matter. SEM models with cross-sections, SSM FG 1 cm cutter, tuned to smooth cusps. Furthermore, the halo's triaxiality, minor to major axis ratio CA FG 0.6 heteros, because 0.8, is supported by velocity anisotropy parameters, BO 0.5 to 0.7, from GC proper motions, indicating radial orbits dominate in the outer regions, consistent with accretion along the cosmic web and providing a natural explanation for the velocity dispersion plateau observed in DS. Hubble's Ultraviolet Quasar Sightline Survey, Project Omega, probing 43 quasars with far UV spectrographs like COS, shows this halo isn't empty. An inner 500,000 light-year zone is laced with metal-rich, metallicity Z 10.6K plasma, stirred by supernova feedback and galactic fountains that eject metal-enriched gas at 100 to 500 km, creating turbulent eddies and density variations, traced by absorption lines of psi watt, ionization potential 45 eV, with column densities NOVV 8 on 14, ton 15 centimeter to meter 2, indicating a multi-phase medium where cool clouds 10-4K are embedded in hot flows, potentially sustained by dark matter subhalo interactions that compress gas and trigger cooling. The outer shell beyond is smoother and hotter, with more uniform ionization, lower NHAN, NOVV ratios, and lower metallicity, suggesting pristine and foul from the intergalactic medium, IgM or recycled material from ancient mergers, lifting Andromeda's baryonic halo mass to 4 by 1011 solar masses, and swelling the total virial radius toward 2 million light-years, far enough that its outskirts have already begun interpenetrating the Milky Way's own envelope at 1.5 million light-years, as inferred from overlapping CGM detections in joint Hubble-Gaia studies. This two-layered structure, with the inner halo showing clumpy kinematically complex flows, velocity widths depth to v at 200-400 kilometers s, and the outer, more laminar, aligns with hydrodynamical simulations, like Fire 2, where supernova-driven outflows, energy injection, and to 51 ergs per event, create a galactic fountain cycle, recycling 50-70% of ejected gas back into the disk over Drabine year, while dark matter's gravitational scaffolding prevents wholesale escape, maintaining a baryon fraction FB a 0.1 NAD 2 consistent with cosmic averages. The halo's mass, inferred from X-ray emissions via Chandra and XMM Newton detecting diffuse hot gas with LX AU 10 to 39 ergs is ALIS, and metallicity gradients from Phi, gravitational lensing, weak lensing, signals from stacked background galaxies in SDSS data, showing shear distortions, G A 0.0.1 at 100 to 500 kpc, with convergence chi A 0. Forming a Navarro-Frank-White NFW profile, with a concentration parameter C A 0.1. Though some models favor a chord profile, Burkhardt or Inesto, with core radius RC A 0.9, potentially explained by CEM self-scattering or baryonic feedback, coring the profile through repeated gas outflows. Gravitationally, this halo exerts profound effects across scales. It lenses light from distant quasars, causing microlensing events that amplify fluxes by factors of 2 to 10 for hours to days. Einstein radius RE, allowing probes of its clumpy substructure, subhalos of 10-6, 10-9 solar masses, predicted by CDM, but debated in warm dark matter. Alternatives with cutoff masses, 10-8N, with event rates 1 per year, per quasar in dense inner halo fields. It stabilizes satellite galaxies against tidal stripping, as seen in MEM32's survival, despite pericenter passages at 5 kpc, where dark matter subhalos provide additional binding energy. M sub in 10-9, M within M32's Roche lobe, and it warps the motions of halo tracers like globular clusters and planetary nebulae, whose anisotropic distributions, velocity anisotropy BA, M, Fa, C into 0.7, with tangential bias in the inner halo shifting to radial in the outer, reflect the halo's triaxiality, with major axis alignments matching CDM simulations of web-like accretion, where filaments channel a 60% of mass along preferred directions, as evidenced by the GSS's alignment with the halo's long axis. On larger scales, the halo's gravity influences Andromeda's place in the local group, tugging on the Milky Way at 1110 km/s, proper motion my 100 my Azar from Hubble, and driving their mutual approach despite Hubble expansion, while its extended reach overlapping with our galaxy's halo at a 1.5 million light-years, suggests intermingling CGM gas with shared metallicity gradients, potentially detectable in future absorption studies with the James Webb Space Telescope, JWST, targeting far UV lines like Lyman alpha or an emission with the Square Kilometre Array, SKA mapping 8. The implications for Andromeda's future merger with the Milky Way, projected in 4.5 billion years based on Hubble proper motion measurements, showing a relative tangential velocity of 17 km/s and a pericenter distance of 30 kpc, with 95% confidence bounds of 0, are deeply tied to dark matter's collisionless nature. Unlike baryonic gas and stars that will collide, shock heat to 10.7 K with luminosities 1043 ergs in X-rays, and form tidal tail, the dark halos will pass through each other, largely unscathed on the first approach. Impact parameter B, 50 kpc, their particles interacting only via gravity, with scattering cross-sections 10 to the 26, leading to multiple passages, 3 to 5 over 2 Ge, where tidal torques strip outer material, greater tidal torques strip outer material, greater 10% mass loss per flyby, and elongate orbits before final coalescence into a single elliptical Milky Way galaxy, with a combined halo mass of 3. During this dance, dark matter's dominance will dictate the merger dynamics. The halo's initial interaction will distort shapes, potentially transforming Andromeda's prolate halo, QAK 1.4, into a more triaxial form, ABC 10, with hydrodynamical simulations like those in Illustriston G predicting enhanced substructure survival in the outer regions, or a 100 kpc due to lower densities, allowing CDM subhalos 10.8c, 10.10 to persist and potentially disrupt stellar streams like the GSS or the Milky Way's Sagittarius stream. Imprinting density perturbations, observable as gaps or overdensities in JWST deep fields. Gravitational heating from these passages will puff up the disks, scale height increasing from 300 pc to 1 to 2 kpc, triggering dual starbursts as gas compresses, rates up to 100 mc, peaking 1 G Ryer, post-pericenter, while the halo's interpenetration could accelerate black hole mergers. P Ryer, P Ryer, keenward over 100 million years, via dynamical friction against the dark matter background. Drag force FDF, keen MBH2 ReCB2, with deceleration, emitting gravitational waves at frequencies 10 to 10, potentially preceded by electromagnetic precursors, like enhanced accretion flares. If gas is funneled inward, dark matter's role extends to post-merger stability. The combined halo will recentralize through violent relaxation over a 100 dynamical times, its prolate shape relaxing to ablate crew at 0.8 through box orbit, scattering and Landau damping, influencing the remnant's morphology, favoring an E3-E5 elliptical with effective radius RE at 10 kpc, and satellite retention M33 may be ejected at 200 km/s if captured in a resonant orbit, with implications for habitability as our solar system gets flung to the outskirts. 90% chance of survival, but relocation to 100-200 kpc in a diffuse stellar halo, exposed to lower dark matter densities, uncertainties abound. Alternative models like modified Newtonian dynamics, Menzies, challenge CDM by attributing flat rotation curves to gravity modifications at low accelerations. A0, Menzies, Men0, rather than dark matter. But Andromeda's halo observations, including the hot gas mass via X-ray surface brightness profiles, fitting King B models with B, A0.5, lensing signals, mass enclosed N-meteor, A0 Parniwendro Parniwas, et are 200 kpc from weak lensing, and satellite kinematics, e.g. NGC-147's orbit, requiring dark matter to avoid tidal disruption, strongly favor CDM, with future tests via JWST or the Nancy Grace Roman Space Telescope, mapping halo gas kinematics, velocity fields to Phi's 50 km/s, precision to distinguish between models by searching for predicted CDM sub-halo wakes or Menon's phantom dark matter effects. This invisible scaffold not only holds Andromeda together, but steers its destiny, a puzzle that could unlock the universe's hidden rules, as we anticipate the grand cosmic collision, where dark matter's ghostly passage will orchestrate a galactic rebirth. And that destiny, it's hurtling right at us. Picture this. In a cosmic timeline stretching billions of years ahead, the serene night sky we know transforms into a theater of gravitational chaos. As Andromeda, our galaxy's massive spiral neighbor, currently 2.5 million light-years away, hurtles toward the Milky Way at 1110 kilometers per second, a velocity measured through its blue-shifted light since 1912, signaling an inexorable approach, driven by mutual gravity within the local group, a cluster of over 50 galaxies, where these two titans dominate with their combined mass of trillions of stars. This impending encounter, long predicted to culminate in a head-on collision around 4.5 billion years from now, based on early Hubble Space Telescope data from 2012 that pinpointed Andromeda's proper motion sideways drift across the sky at less than 0.1 milliarc-seconds per year, would not be a sudden cataclysm, but a protracted gravitational tango, lasting hundreds of millions of years, with the galaxy's dark matter, halos, vast, invisible envelopes, extending hundreds of thousands of light years, interpenetrating first their collisionless particles, passing through each other, while exchanging momentum through dynamical friction, a process where denser regions slow the orbits like cosmic brakes, gradually drawing the luminous disks closer. In the classic simulation scenario, the first close passage occurs in about 4 billion years, with Andromeda swinging by at a pericenter distance of roughly 100,000 light-years, comparable to the Milky Way's diameter, unleashing tidal forces that distort both galaxies' spiral arms into long, arcing streamers of stars and gas filaments that could stretch millions of light-years, as seen in N-body hydrodynamic models, incorporating 10-8 particles to track stellar dynamics and gas hydrodynamics, where gravitational torques rip material from the disks, flinging it into intergalactic space, or back inward to fuel massive star formation bursts. These bursts, peaking at rates up to 100 solar masses per year, 10 times the current Milky Way rate, ignite as compressed gas clouds collapse under the added pressure, birthing clusters of hot, blue stars that illuminate the merging system like fireworks, with supernova rates spiking to create heavy elements and drive outflows that enrich the surrounding halo, a process replicated in simulations like those from the Illustrist NG project, which show such mergers doubling the stellar mass through triggered star formation over 1–2 billion years. Yet, this dramatic narrative is no longer set in stone. Recent 2025 analyses combining Hubble's precise astrometry with Gaia's parallax and proper motion data for millions of stars, alongside updated mass estimates for satellite galaxies, reveal substantial uncertainties in Andromeda's trajectory. Its tangential velocity lattice to the Milky Way could be as low as 17 kilometers us, or up to 200 kilometers us, depending on error margins, slashing the odds of a direct merger within 10 billion years to about 50%. A coin flip revision from near certainty that accounts for the gravitational perturbations from third parties, like the Large Magellanic Cloud, LM mass 10^11 solar masses, pulling the Milky Way slightly off course, and Triangulum, M33, 5 by 1010 solar masses, potentially joining the fray or being ejected. In roughly half the 100,000 Monte Carlo simulations run with these refined inputs, the galaxies execute a flyby at distances greater than 500,000 light-years, losing insufficient orbital energy through dynamical friction for a prompt merger, instead entering elongated orbits that could persist for eons, or even indefinitely, if the initial miss is wide enough. As dynamical friction weakens with distance and the expanding universe's Hubble flow, K/0, 70 km sev, can BC, adds a subtle outward push. In the merger favoring half, the first encounter, now projected with a 2% chance of being truly head-on, stretches the galaxies into tidal bridges and tails, with Andromeda's more massive halo, 1.5 × 10^12 solar masses, dominating the interaction and stripping the Milky Way's outer disk, flinging stars into vast streams that wrap around the pair like cosmic ribbons, as visualized in high-resolution N-body runs where 10^9 particles track individual stellar paths, showing 10 to 20% of each galaxy's mass redistributed into a diffuse envelope. Subsequent passages, occurring every 1 to 2 billion years as orbits decay, amplify the chaos. Gas shocks heat to millions of degrees, emitting X-rays detectable across the local group, while compressed molecular clouds birth OB associations and superstar clusters, potentially forming 1010 new stars in bursts that outshine the galaxy's steady glow, with supernova feedback, ejecting metals and driving galactic winds that could quench further formation in the remnant's core. By 6 to 8 billion years in, the galaxies fully coalesce, their supermassive black holes, AIM-31 at 140 million solar masses, and Sagittarius A at 4 million, forming a binary that spirals inward over 100 million years, via dynamical friction against surrounding stars and gas, eventually merging in a burst of gravitational waves at frequencies 10 to 4 nm, detectable by future observatories like LISA, with strains of 10 to 4 nm releasing energy, equivalent to 10 or 5 supernovae and potentially kicking the final black hole at 100,000 km. The end product, Milkdromeda or Milkomeda, emerges as a giant elliptical galaxy with a mass of 3 × 10^12 solar masses, its spiral structure erased into a smooth reddish spheroid, effective radius 10 kpc, dominated by old stars, though lingering gas pockets could sustain low-level star formation for another billion years, as seen in merger remnants like NGC 7252 with its young clusters. For our solar system, the odds favor survival. Stars are too sparse for collisions. Average separation, but tidal torques could relocate us to 100-200 kpc from the new core. 90% probability, exposing Earth to a night sky ablaze with Andromeda's stars filling the view, perhaps 100 times brighter than today, while the Sun by then, a red giant, engulfs the inner planets, rendering the merger a distant spectacle for any far future observers. Triangulum's fate adds intrigue. In 40% of simulations, it joins the merger, contributing its 5 × 10^10 solar masses and potentially forming a triple black hole system before ejection or merger, while in others, it's flung out at 200 km/s to wander the local group as a rogue galaxy. The LMC, meanwhile, could survive as a bound satellite, its orbit perturbed into a wider loop, influencing Milkdromeda's asymmetry. These predictions hinge on dark matter halo's collisionless nature, allowing pass-throughs that prolong the dance. But uncertainties persist. Gaia's DR3 data refines Andromeda's proper motion to -0.46, -0.56, -0.5. But error bars permit scenarios where the galaxies recede after a graze, especially if the local group's total mass, including Virgo cluster influences, is underestimated, pushing the merger odds below 50. High-resolution simulations like those from Fire 2 incorporate hydrodynamics, showing gas bridges forming between the galaxies during flybys, potentially birthing intergalactic stars and enriching the CGM with metals. While magnetic fields, BZ10 could channel outflows and suppress mixing. In non-merger paths, the galaxies might form a stable binary, orbiting at 500,000 light-years with periods of 10 Geri, their halos merging partially while disks remain distinct. A slow dance that delays Andromeda indefinitely. Regardless, this event will reshape the local group, potentially ejecting dwarfs like NGC 6822 and forming a more compact cluster, with JWST and Roman poised to test predictions by mapping progenitor streams today. Andromeda stands in our telescopes like a time-lapse portrait of everything the Milky Way has been and everything it may yet become. A galaxy so immense that if you could swap it with the full moon, its glowing disk would spill across 6 full moons in width, each rim spanning 1 light-years of star. Its trillion-star bulk is girded by a dark matter halo, more than 1,000,000 light-years wide, a hidden scaffold 5 to 10 times heavier than all its luminous gas and dust combined, strong enough to keep those outer arms from flying apart, even as they orbit slip inside that halo, and you find a central bulge packed with ancient red giants, a doubled nucleus circling a 140 million solar mass black hole, and spiral arms studded with newborn blue clusters and the unpredictable tantrums of luminous blue variables. An entire cosmic life cycle playing out in one colossal arena. Its chemistry reads like a galactic autobiography. Hydrogen clouds primed for new stars, carbon-rich AGB elders sprinkling dust, metal-poor halo relics whispering of the universe's dark ages, and tidal streams strewn with the isotopic fingerprints of long-devoured dwarf galaxies. Rare stellar misfits, Wolf-Rayet cores stripped bare, hypervelocity runaways racing for intergalactic exile. Even magnetars with trillion Gauss fields crowd the exceptional catalog that only a galaxy of Andromeda's size and merger history can host. Beneath that fireworks show, an invisible legion of black holes keeps silent. Score, a quiet supermassive anchor in the core, a possible swarm of intermediate mass beasts hiding in globular clusters, and untold millions of stellar remnants roaming the disk and halo, all woven into a dark matter web that dwarfs the starry tapestry we can actually see. Andromeda's very motion turns the telescope into a time machine. Its blue shift tells us the gravitational story isn't static, but speeding toward drama. A closing velocity of about 110 km. This means that unless new Gaia-era simulations prove otherwise, our 2 great spirals will begin a slow-motion ballet, roughly 4 billion years from now, exchanging tidal tails that could wrap halfway around the local group, sparking bursts of star formation bright enough to rival quasars, and quite possibly merging into a giant elliptical dubbed Milkdromeda. Some 6 to 8 billion years hence, even the latest coin flip studies that lower the certainty of a direct crash still concede that our dark halos have already started to mingle, guaranteeing that Andromeda will keep sculpting our future one way or another. For humanity, that cosmic forecast is both humbling and invigorating. Unless we abandon Earth well before the sun's red giant phase, no living eyes will witness the final fireworks. But the story matters now because it reframes our sense of place. When you look up at that faint smudge in Andromeda's constellation, you're seeing a mirror held 400 billion times farther away than the full moon, yet reflecting our galaxy's destiny in real time. Understanding it unifies chemistry, gravity, and cosmic history into a single narrative arc that eventually sweeps us in. So if this journey through Andromeda's secrets set your curiosity spinning, transform that wonder into action. Hit like so the algorithm launches this story. To fellow stargazers, subscribe for more deep dive expeditions that keep your imagination in orbit, and fire up the comments with your biggest cosmic what ifs. Will the Milky Way and Andromeda slam together on the first dance or waltz forever? Could future humans hitch a ride to a safer vantage world? Your questions steer the next episode, and together we'll keep chasing the universe's unfolding saga.